So is there anybody here that does not understand Spanish? Okay, you can go through the exit. No, just kidding. I will do it in English. First of all, thank you to all of the sponsors and organizers for making this event possible. And before we start, how many of you have worked with ACID transactions in a monolith? Or in any application?
With or without?
With. Okay. How many of you have worked in a distributed system? Okay. Did you miss global transactions across service boundaries? Kind of? Okay. So I hope you find this talk useful. Here we go. Okay, that's me. I'm Rubén Pérez. I'm a software engineer at Shipstead, Spain. That's my Twitter account. And also I work mostly with Java, but I'm not a Java champion. Sorry. I have written 0 books. Sorry. This is also my first talk. Again, I'm sorry. But bear with me. I will try my best. So let's go. In this talk, we will be briefly talking about ACID transactions and why they are not an option in a distributed system. Also, we will see what is the two-phase commit protocol and why we should avoid it. And then we will get to sagas and why they are a good option here. So here we go. So lots of us have worked in a monolith. And there we have that magic thing that are ACID transactions. So we can execute more than one command to a database in an atomic way. We can just begin a transaction, do whatever we need in there, and end the transaction. And either everything completes successfully, or the database will be left in the same state as before. But what's ACID here? ACID are a set of properties of database transactions that are intended to guarantee the validity even in the event of errors. So ACID is an acronym that stands for atomicity. That means that all or nothing, everything will be executed or the database will be left unchanged. Consistency, that ensures that any transaction will bring the database from one valid state to another. Isolation, that given that we execute our transactions in a concurrent way, we will end up with the same state as if they were executed sequentially. And also durability, that once we commit a transaction, it will remain so even if there are errors there, or power losses, or whatever. So far, so good. If we work in a monolith or in any application and the product is successful, it will keep growing. And if it's successful for a long time, it will be growing for a long time. So it will get worse. So we can end up with code bases like those that are really a big mess. They have a lot of duplicated code. There's a high coupling in there. You are afraid, almost scared of changing some parts of the system. It's almost impossible to refactor because there are no tests in there. So how many of you have worked in code bases like those? Okay. How many of you have worked in more than one like those? Okay. So you get my point. So if you are brave enough to change anything there, you may end up breaking something. It may be even part of the system that you thought it was completely unrelated to the one that you were changing. But that's what happens with those code bases. And also, if you are really, really, really unlucky, you could end up with a situation like that. So working in a code base like this, we can see problems arise. So they are high coupling. It's too large for a single developer to really understand. The development is slow day to day. you end up with a spaghetti code or a big ball of math or big ball of whatever word you want to put in there. And also you have the delayed deployments. You have reliability issues because any bug or leak in some part of your system will harm you and bring the whole system back down. And also you have long-term commitment to a technology stack and so on, and many, many, many more. So what we would like? We would like to have smaller code bases. We would like to have less code complexity and a code that is faster to develop and easier to understand. And also minimize the cost of change, and also place different responsibilities at different services. Also, we would love to deploy them independently. It would be nice to have to be able to scale those systems better, and so on. So we move to microservices, either because of any of those reasons or because they are trendy and they are cool. You choose. So we have our example application that is a microservice application for trips, for a trips application. So we have a microservice for a car rental service, another for the hotel booking service, another for the payment, and another for flights. And you can have as many microservices as you need, or that you want, or that you whatever. So we have moved to microservices. Everything is great. We are super cool. And we are fun, and we will be fun forever. But not so fast. Everything is a trade-off. Moving to microservice implies that we are getting a huge amount of complexity, an increase of complexity that is pretty huge. For example, we don't have ACID anymore across service boundaries. So we cannot do just begin transaction and start calling different services across service boundaries and end transaction anymore. So what can we do now? First, we have the first option that is a two-phase commit. So what's two-phase commit? Two-phase commit is a specialized type of consensus protocol, and is a distributed algorithm that coordinates all the processes in a distributed transaction on whether to commit or abort, or rollback in this case. And for this protocol, we have a new player that it's the two-phase commit coordinator that is in charge of coordinating things. And we also have two phases. The first phase is a commit request phase, in which the coordinator sends a query to commit request to every one of the participants. And the participants have to vote on whether they will fulfill the request or not. So we will see the second phase is the commit phase, in which we get the request from the coordinator. So each service has to either vote yes or not, depending on whether they can fulfill or not the request. And how do they do that? They open a transaction in each service. You can have ACID transactions there. You open a transaction, you do all the work in that transaction, but you do not commit that transaction. So you know for sure if you could fulfill the request or not, and then you answer back to the coordinator. In this case, every service can fulfill the request, but if you see here, given that we are not committing the transactions, we are holding logs. Holding logs and blocking resources throughout the whole protocol. So the coordinator once gets all the votes. If they are all yes, it will send a commit request to each participant. And once they get that commit request, they can commit the transaction and acknowledge back to the coordinator. And now they can free up all the resources that were kept blocked throughout the whole execution. So another scenario in which one of the services answers no, as you can see here, given that he's not doing anything, there's nothing blocking here. So if the coordinator gets any no as a vote, it will send a rollback request to each participant, and all the participants will roll back that transaction. So we acknowledge back. So the system is exactly in the same state as it was before. But we're holding blocks here, here, and here. So for this protocol, the two-phase commit protocol provides atomicity because all the commits are applied at the same time, or no commit is executed at all. And also from a developer's perspective, it's very appealing because it's quite easy and it's almost the same thing as if you had the same old transactions. But there are a lot of cons here, important ones. So it's a blocking protocol. So you move to a distributed system because you needed better scaling, but you are holding block throughout the whole execution. So it does not scale, so it's not really a good option. Also, the two-phase commit coordinator is a single point of failure. And that means that if they die before sending the commit or the rollback request, you will get into big troubles. Also, in the worst case scenario, including retries, you can have a quadratic cost. And also, you get a reduced throughput due to the logs. And also, you are depending on the slowest machine, not once, but twice, because there's two phases there. And also, two-phase commit impacts availability, because the availability is the product of the availability of all the participants in the transaction. So the more participants you have in a transaction, the less availability will your system have. So
what happens if a commit fails?
If a commit fails, which commit? The commit of the transaction.
No. When you commit, you get the SDK.
Yeah.
You say, okay, all of you commit.
No. I will go back.
If one of those fails.
If they vote yes, it means that they open a transaction. They already did all the work, but they didn't commit the transaction.
Yeah. And what if?
And now, if we send a commit request, then they will commit the transaction.
Exactly. But let's say that one of those four failed right now.
Mm-hmm.
One of those four commits will not be committed.
It's kind of weird scenario because the transaction has already completed all the work. All the work. Sorry.
But it's not committed.
Yeah, but if the transaction if the database is not dying, you will not face that problem, as far as I know. If the database die, I mean, you probably will have more problems than that. I'm not sure if
I mean, either database or a service, doesn't matter really.
Sorry?
Either database or a service you're committing, sending a commit request to.
I'm not sure about that, because if the transaction was already created and was already stored in the database, not at the application layer, but at the database layer, but without the commit.
So another instance.
So you shouldn't.
Take over.
Yeah, that's the point.
Sorry, one question. When you say that it's blocking,
Yeah.
what do you mean with that?
With blocking. For example, if I'm asking for buying a ticket to a flight, depending on your database model, you may end up blocking rows of your database, so you could not answer any requests that are trying to work with those rows until you unlock the resource.
But that's up to how you implement the
Yeah, kind of. But if it mainly the big point here is in your database. It depends on your isolation level there. If it's strict, then you will not be able to do anything with that until the transaction commits or rollbacks. So we were here. So this is not really a good option and does not scale well. So can we do better? You bet, because if we couldn't, I wouldn't be here. So here comes SAGAS. What's SAGAS? SAGAS was a paper from Héctor García Molina and Kenneth Salem, and it was related to the database world. And it was from 1987, so it has already 30 years old. It's quite old. The paper was dealing with long-lived transactions and how to improve the work for them. Long-lived transactions are transactions that take too much time to execute, either because there are higher, complex calculations to do there, either because they hold a lot of data, or even 30 years old, they were waiting for user input. So what's a SAGA? SAGA in this context is the context of this paper, because there are sagas in JavaScript and in many other languages that are a different thing. But in this context, sagas are long-lived transactions that can be broken up in a series of independent steps. So either you can succeed executing each one of these steps, or compensating transactions will run to amend partial executions. So what do I mean with that? We have a global transaction that we have split into some steps that are kind of atomic. And we have to provide for each one of those steps, we have to provide a compensating action to undo the previous work. And the key point is here. The compensating transaction semantically undoes any of the actions performed. It does not necessarily mean that you will get the exact previous state of your database. It just means that will be semantically equivalent. For example, if one of our steps is adding 1 to a given number, the compensating request will just subtract 1. But if you are making a payment, you cannot undo a payment. The compensating action here could be to refund that payment. But if you see your bank account, you will see 2 steps. The state will be semantically equivalent, but because you will still have the same amount of money, but you will see the 2 steps there. And another example will be that any of our steps sends an email. You cannot unsend an email, so you may end up with a compensating action that is just a follow-up email explaining the situation. So in a formal way, sagas guarantee that either each of our steps completed successfully, or if one failed, we will start compensating all the previous work. And in a more visual way, if our transaction has action 1 that completes, action 2 that completes, action 3 that failed, now we have to undo the work of the action 2 and undo the work for the action 1. In our trips application, that will mean that after a saga execution, we will either have all the steps completed, or if any of those fail, we will end up with a semantically equivalent state in our system, but it will be consistent in either way. So we can see the sagas are a failure management pattern. And also, we can see the difference in the approach of the 2 options. With two-phase commit, you have a global atomic distributed transaction that takes longer to complete, and you are holding resources there. And here, with sagas, you can split into individual steps that can be run whenever you want. And the saga protocol will take care of the overall consistency. But a saga does not have ACID guarantees. It's not atomic. Mainly because you can start a saga, execute the first step, and the result of that execution would be visible even if you have not completed the saga. In this case, you will not see the result until you commit all the transactions. And also, regarding isolation, it does not provide the strict serializability because it's not atomic. But the trade-off here is availability. We will end up with a huge increase of availability in respect to the two-phase commit. So up until here, we have been discussing sagas as an architectural pattern. Now we will get into design choices to make in order to implement that. First, the typical choreography versus orchestration choice in a distributed system. The orchestration has a central component or a central process that is a coordinator that handles all the interactions between the service. And with choreography, you don't have any central component for pretty much anything. And it's usually message-driven, and it usually have some kind of hidden rules, because somehow you have to still complete flows, but without a central component. So after any of our steps complete, some code has to decide what to execute next. It could be the next step, or it could be a compensating action to a previous one. So the first option is choreography. If our flow has 3 steps, I don't need any central component. Just my saga will get to the A step, will get it executed, will continue to the B step and to the C step, but without any central component handling the flow. So with choreography, we have a distributed decision making, and also we have some pros that we don't need an extra component to implement that, and we also have a higher flexibility to add new sagas, mostly depending on the implementation details. And also a few cons. Each service has to know what to do next, and yet that's beyond the scope that it should have, because we are breaking a single responsibility principle here. And also we are increasing service coupling, because the logic about the saga is scattered throughout the system. So as always, it's a trade-off. Another option is orchestration. Sorry. Here we have a central coordinator, a central component that is in charge of handling the interactions between the services and handling the flows. So here we have a centralized decision-making component, and also we have some pros that we have better visibility of processes and ease of management. Given that we have an actual component for that, it's quite easy to monitor that, it's quite easy to alert from that, it's quite easy to extract metrics from that, to draw dashboards if you want to. You can do whatever you want because it's an actual component. And also you increase cohesion and you have better composability. We will see an example later on of that, but the idea is that you are letting your components to be more atomic because they don't have to handle the flow of the saga. And also you are creating a coordinator that its single responsibility is to coordinate and to handle those flows. So you are having higher cohesion throughout your system. And as a con, you need a new component, or at least a new implementation in an existing component, and you should need to write new code in that component in order to support new sagas. So, as a personal opinion, I would rather choose choreography if my system requires a lot of new sagas constantly, because we can, depending on the implementation, but if you choose routing sleep with, there's an enterprise integration pattern that it's called routing sleep. If we choose to implement with routing sleep and context passing, you could end up with services that they only have to know that they are dealing with sagas, but they don't have to know the details. So if you end up creating new sagas, it will be self-contained. So you can implement a new saga message without all that logic inside of it, so the services wouldn't require any changes. But if you have a normal application in which you are not delivering features daily, I would rather choose orchestration because of this. Because you can see, you have better cohesion and better composability, and also you can extract a lot of information from your system. So for the orchestration, there are 2 typical ways of implementing that. The first one would be that the orchestrator is an already existing component of your system. And you can see some examples of this from Chris Richardson. If you don't know, Chris Richardson is the guy that is in charge of the Microservices.io. And also there's another option that is that the orchestrator is a brand new component. And that was introduced, I think, by Katie McCaffrey from Twitter, Microsoft, Halo, and many more. So this last one is the one that I like the most for common applications. So we will dig into detail of this one from now on. And we can call that SAGA execution coordinator. So in this approach, we have two main components. The first one is a distributed and durable log that has to be fault tolerant and highly available. You can use Kafka or Kinesis or whatever you want to use. And the second one is the SAGA execution coordinator. It's just a normal application that you can write. So now we are going to define some characteristics of the requests. So here, first the compensating request. So for this approach, the compensating request must be idempotent. You have to be able to retry them until they succeed. It's like the delete verb of the HTTP. It's like semantically idempotent, so it's not a weird thing. And also the compensating request cannot abort. And abort in this context means that the service answers with a no, I'm not doing that. So if in the case of the hotel reservation service, if you have booked a room there and you want to cancel that, the service cannot say that they are not doing that. So those are the preconditions. And also, now the requests. The first one, they must be idempotent. What do I mean with that? They must be idempotent unless you can afford them to not to be. So for example, if I send a request to a service and I don't get a response back, if I'm able to cancel or to compensate for that without having that response, then I can live without idempotent requests. But if I don't have that capability, my request must be idempotent. Any doubt? Yeah? It's a kind of tricky? No? Okay. The request can abort. That's perfectly fine. I can try to buy tickets for any flight, and I can get a response that I'm not doing that because there are no seats available. That's fine. And also the request should be commutative with the compensating request. So commutative here means that 1 plus 2 is the same as 2 plus 1. So why do we know this? Let's see an example. Imagine we are in an application and we have a client to send request to a hotel service. And we send a request to book a room. But we are in a distributed system, so we get timeouts. You should get timeouts if you are handling timeouts. We get a timeout, so we don't know what happened there. We don't know if the request got to the hotel service or not. We don't know if the request got completed successfully or not. We don't know anything here. So given that our requests are idempotent, I can retry that. And the request succeeds. So I have my room booked. But now, for whatever reason, I need to cancel that. Maybe because any other of the steps of the SAGA failed. Now, I cancel that room, and everything's fine. But we are in a distributed system, bad things happen, and we have a synchronous network, so now the first request gets to the hotel service. So if they are not commutative, you will end up with a room that you don't know that you have, and that you don't know that you should cancel that because you don't know that you have it. But that's not just for sagas. That case can happen in any distributed system, and I think we are not used to deal with it, and we should. So let's see some examples. I think it will be easier to understand. Here we have our SAGA log. Here we have our system and our user. So our user sent a request to our system to get a whole trip. So it gets to the coordinator, and the coordinator starts a new SAGA in the log. Now, it starts the first step, writes that it's starting the first step to the log and send a request. For the sake of brevity here, if you see the same transition, we'll write to the log and send a request. But you must first write to the log and then send a request. Because if you don't do that, you will end up in trouble. Because You will send a request that you don't know that you have sent it, and it's the same problem as before. So we send a request, it succeeds, we get the response back, and we write to the log that we have completed the task. Then we can move on to the next. And also here, I write start card and end card, but you can put in there whatever you want. You can log whole requests and response. It's up to you. So we continue to the next step. We start the hotel request, succeeds, we get the response back. The same for the flight. We get the response back, we write it to the log, to the payment service, same thing. And now we end the saga. So that's how it works. And this is the happy path. So now let's see some other cases. Is there any doubt up until here? No? Okay. Now, another scenario. The same flow, send the first request, succeeds. Send the second request, succeeds. We send the third request, and it fails, because there are no seats available. So what do we do now? We have to write to the log that we are aborting the saga, and also we are aborting the saga because the flight request failed. So now what do we do? We have to check in our log which steps got completed. In our case, we have the car step completed and the hotel step completed. So we have to compensate for them. So we have to send a request to the hotel service to cancel that room. It succeeds, so we write to the log that we have compensated for that. Same thing for the car service. We have compensated for that, so we have completed all the compensating flow, and we end the saga.
So what's happening if you can't compensate the hotel?
If you can or cannot?
Yeah, you cannot.
If you cannot?
Yeah.
If you cannot,
the network issue, whatever.
you must retry.
You keep the saga contractor in the SAG server, and then when they become available again, you just finish the...
It's up to you. You have to retry until it succeeds, because as a precondition, it cannot abort. Okay. So it's a matter of retry. And it's up to you if you are using this protocol in a message-driven application or in a request response application. It's up to you what to do with the user. But in order to guarantee consistency in your system, you have to complete the saga. So now, yeah.
So I understand the retries.
Can you?
I understand the retries.
Yeah. Okay.
Retries, whatever. But what if while we're doing the start flight, something goes and changes the car database, so that the compensated car actually physically cannot, no matter how many times you try, because you change the database and the SQL statement account fails. How does it work in that situation?
Yeah. It can happen with. It's easier with a hotel room service. The example that you are making, I think. If you cannot cancel a room, it's hard to me to not be able to cancel anything. It's easier to think in the case of you are not able to succeed with a request because any other saga has got there first. So if there's just one room available and you are trying to execute your trip saga and I'm doing the same thing, the first who get there will get the room. And given that the protocol is not atomic, maybe you get the room, but you have to cancel that because whatever reason, but I still didn't have my room. So that's the issue with not being atomic. I'm not sure if I've answered. Okay. Any other question? No? Okay. So in this scenario, we are semantically, our system state is semantically equivalent to the previous one. And in another example, we are succeeded completely, so we are fine. Another case. Same thing, we send the request, we start the saga, send the first request, complete, succeeds, send the second request, and we get the timeout. So what do we do now? given that our requests are idempotent, we can just retry until it completes, either succeeds or aborting. Now it succeeds, so I can move on from there. I logged that I completed the hotel step and move on from there, the same thing as before. And I complete the flow and end the saga. So here, if I get a timeout here and my requests are not idempotent, I have to be able to compensate for that even if I didn't get the response back. For example, if we have a communication in two-step, for example, I create an order, then I complete the order or execute the order itself, and in the first request, I just get an ID, an order ID or something like that. If I got that, I wouldn't need my request to be idempotent because I would be able to still see the state and see if I can retry that, or if I cannot retry that, I should cancel that. So yet another example. Same flow. If this works, okay. I send that request, succeeds. Now I send a second request, and I send a third request because it's not mandatory to be to send requests in a sequential way. I can do whatever I want. So I send those requests in parallel. And now the flight request fails. So, and also, no, sorry, spoiler. And the flight request fails. So what do I do now? The first thing to do is to abort the saga and state that my flight request failed. And now I also know that I did get a timeout from the hotel request. So I know that I should roll all the work back, but I have kind of weird state here because I have completed the car step. I have a start hotel here, but I don't have an end. So I don't know what happened. I don't know if my request executed successfully or not. So I don't know what to do here. So given that my requests are idempotent, I can just retry until it succeeds. And I write to the log that I have completed the task. Now that I have completed the task, I know that I have to undo that. So I send a request to compensate that. That succeeds, so I have compensated the hotel request. Now I do the same thing for the car service. I write it to the log, and I end the saga. Do you have any doubt about this?
So you say that your compensation is idempotent. So why
Yeah.
do you just not cancel?
So you mean
So why you
here?
try? Yeah. Why do you just
Because I don't know what happened. But I don't know if I even have a booked there.
But you can cancel.
Yeah, but I cannot cancel a thing that I don't know if I had that.
Because you need the context.
Yeah, either my requests are idempotent or I have to be able to do what you say. But in this case, I'm not able to do what you say. So I can retry until I'm sure that I have completed the task. So now that I know that for sure, I can compensate for that.
But
Yeah, there's always a but.
yes,
Thank you.
what I'm watching here is okay. Those scenarios are fine. But the thing is the retry storm that you will. Let's say the booking is not available, and it suddenly after 2 hours it becomes available something, and let's say this is acceptable for the kind of service. So
Here you
the
can have
retry-
ACID in each service. That's fine.
The retry storm is going to be crazy
Yeah.
for this one, and maybe you are starting getting timeout. So at some point you have to stop and just undo everything else. I'm saying in the sec.
Yeah, you can compensate in parallel if you want to. But until that compensating is finished, you will not finish the saga. But you can just time out the process to the user and say, I'm not completing this,
Yes.
and you just retry using back off or not or whatever. But that
A number of
you can do
times,
that.
just you don't kill
Yeah.
Okay.
You can do that. Any more questions? No? That's it? Yeah?
Anyone that is responsible of, let's say, coordinate everything is the central executor, right?
Yeah, this one is in charge of dealing with the flow. So it has to know what are the steps that belongs to the saga and which ones have completed or not. But the state is in the log. So you can have the state replicated here, but the single point of truth of your saga executions are in the log. So I'm not spoiling you anymore. We will get there. But have I answered? Okay. Okay, so now we're getting there. We saw that the two-phase commit coordinator was a single point of failure. So what happens is if our coordinator fails. So for example, if we have just one machine for this, for whatever reason, if we just have one machine and it goes down. So what happens here? Down in any way. So given that the state is in the log and it's not in that machine, you are perfectly fine because you are not losing anything and you are not losing consistency. So in this case, the coordinator is not a single point of failure, and you can have as many of them as you want. That's an implementation detail that you have to decide what to do. So if it fails, you can just spin up new machines or reboot your actual machines or do whatever you do with your infrastructure. But also, once it's up, the service is up again, you have to resume the previous work. So we have to deal with a few scenarios here. The first one is that every step in the saga execution has a start and an end log. So you are sure that each step succeeded, so you can just move on and complete the steps that you have not executed yet. Next one, we have any sub-transactions with a start but not an end. So you don't know if that completed or not. In that case, we do the same thing as before. We retry until it succeeds and then move on from there. And you can have an aborted saga. So if you have an aborted saga, it's the same as in the examples before. You have to see which steps completed and that you are not compensating yet, and compensate for them. So, as a wrap-up, sagas, this implementation of sagas allows us to have a higher cohesion in our system and more composable services. For example, if our application was just for car rental, we can have two microservices, one dealing with car rental in atomic way and another for the payment. And we can have the flow of the two-step flow implemented in the coordinator. So in this case, that will be the request flow, and this is our dependency graph. And if we need to add a new feature, like a booking application, we just can implement a booking service and a new saga with the two steps, the booking service and the payment. And the dependency graph will stay simple. The same thing with the plane. And also, if you now have to implement a whole trip feature, you still have the same dependency graph. You just need a new saga implementation there. So we can have this implementation of saga or nothing at all. So we get a request, and we have to provide the functionality to rent a car, or buy flight tickets, or book a room. So we have to be able to send requests to those three services. But also, those three services need to send requests to the payment service. And also, they need to deal here, and here, deal with what to do if the payment succeeds or if the payment fails. And also, if you need to provide the feature, or the whole trips feature, you need one of the services to send requests to the other services. So your dependency graph is kind of messy, not the player. So another approach could be to have a trips service in charge of the trips feature. in this case, we still have these 3 requests and those 3 services still have to deal with requesting to the payment services and also dealing with what to do if the payment succeeds or fails. And also, we need to send a request to the trip service, and the trip service needs to be able to send requests to the 3 services. And here, we also have to deal with what to do when each of those requests fails. So here, we have the complex code that is dealing with global transactions and flows in the coordinator. And here, we have that complex code throughout our whole system. So we can see the sagas allows us to have transaction-like flows, also composable services, also increases our cohesion in our system, and also helps us to isolate complex code. And that's it. Thank you. And if you have any question, I will gladly try to answer them.
Okay, I'm sorry being a pain in the ass, but
No.
going back to the failure scenarios, please, to the very last example. So there is still one that I'm not. So I think there is missing there. There, that's perfect.
Okay.
So let's say the coordinator starts the SAGA transaction log, and there is is able to reach one of the actors there, so in the flight, and actually the call gets there. I mean HTTP request, but then network issues happen.
Yeah.
Meaning, in the database it's okay, but the SAGA is not getting any answer.
Okay, you can retry that because the request is semantically idempotent. So
exactly. Okay, I can keep retrying.
Yeah, if the action it's like a delete request. If you delete a resource and you try to delete again, you will not delete anything else, but you will get the same state in your system. So that's perfectly fine.
So you'll need to handle those, like an ID, token or whatever is needed to identify that specific record that you are trying.
If you are trying to book something, you will need what are you trying to book. So there are a few techniques to enable idempotency, at least semantically, so you can choose whatever you want.
So then it will retry and it becomes active, so what will happen is I will retry, I will get through to the database and the database will say, oh, it's okay, I already have it, and I will answer it.
Yep, that's fine.
Okay. Thank you.
Any more questions? Yeah.
Are you using your own implementation of sagas, or do you use open source?
As far as I know, Chris Richardson said that he will release an open source project that I haven't seen yet. I don't remember the name, maybe TAR, but I'm not sure, with an implementation in Java for this. But we are not using it yet because in our case, we don't have to handle global transactions in microservices yet, but we will. But I'm not sure the name. But if you want to look for it, look for Chris Richardson, and in a talk he said that he will open source a project for this in Java.
One example. You say that two-phase commit is not scalable.
Does not scale well. Yeah.
An example where you use two-phase commit. A good example.
If you see an example of that, they may be wrong. So if you are in a distributed system and you choose techniques that locks resources, it's not really wise. In a lot of cases, there may be scenarios in where you need that because you need atomicity, and the solution does not provide atomicity. But if you don't need that, you should run away from two-phase commit.
Okay, question. I am not sure if it's the same that he said, but for example, when you start a flight and you cannot log it, start flight.
Log it here.
Here.
No, given that you first have to log the step in the write the step in the log and then send the request, you cannot send the request before writing to the log. Because if you send the request before writing to the log and something happens and you don't write it to the log, and if the request succeeds, you're fucked.
And when you end the code, the same. You have to, if you
Yeah.
don't have control with the log,
So if you're going to do something, you have to first write it to the log. And if you got something from an external service, you have to write it to the log, because that's the single point of truth. If you do something that you haven't write it here, you are in trouble, because eventually it will bite your ass.
Because wouldn't the idea of orchestrator fit very nicely into ideas behind Raft protocol?
Maybe, but the Raft protocol it's not really easy to. Well, it's easier than the Paxos, but I haven't dig into detail to
I'm
that.
not saying that you should write the Raft
Yeah,
protocol
okay,
itself,
okay.
but use one of those, right? But no, just wondering, kind of. Isn't that kind of like?
I'm not sure, because I read about Paxos, but I cannot remember. I'm not sure. But what I think is that the Raft is easier than the Paxos. That's
No,
what
but
I
in
think.
any case, you wouldn't
Yeah.
be implementing it. You would
Yeah,
be
I hope so.
part of the library side, otherwise.
But I don't know.
Can you give some other example when choreography is better than an orchestrator?
Yeah, it's not really easy to explain this. Using the routing sleep and also the context passing, you can kind of encapsulate the whole SAGA process in a SAGA message. So you can create as many as you want, because those services here will not have to deal with what to do exactly. They don't have to know what to do. The only thing that they have to know is dealing with sagas. But the flow itself is wrapped in the saga. So if you need to constantly implement new sagas, I'm not sure if it's easier, but maybe it's wiser, because you don't have to deploy many components and code what to do with this particular saga in many services. So that would be, for me, if you have a scenario in which you have to all the time create new saga implementation, I would choose choreography for that. But in a regular application, you are not, at least in my experience, you are not creating new features, new big features daily. So I would prefer this one.
Wouldn't that choreography be like a distributed choreography in some way? Because
This.
The choreography will be like a distributed orchestration, because each note should know in some way.
For example, if you have a process with 3 steps, and you have that when you complete the first step, you will emit an event stating that I have done this. Then the second service has to know that when you emit that event, they have to trigger their action.
So this is a message-driven.
Yeah, but you can have message-driven here if you want to send in commands. But still the flow is handled by a certain central coordinator. If you don't need a central coordinator, then you can move it out of the picture if you want. So, Victor?
If those control flights and cars, they're microservices, and I assume that you're talking about microservices on the backend side only?
Yeah.
Right?
I'm a backend. I'm a backend, so that's all.
Kind of like
That's
how would you put all that together with the frontend? What if frontend is a part of that microservice? If you understand what I mean?
I don't know. Yeah, but
Provides
but
frontend part and backend as well.
yeah, but what you make your users see is part of the user experience. But you still, at the backend side, you are providing the guarantees that everything executed successfully or the state is consistent.
Yeah, but I mean, if there is a page that has, kind of book a bottle, book a flight, book a this, and then actually those are 3 dependent components that each sends a different request.
But it's a choice. Either they send out 3 requests, but then you are decomposing the flow and you are handling the flow from the front end. But if you send a unique request for the whole trip, then you will handle that internally in your backend, and then you can apply this. Because if you send individual atomic requests, you have. I'm not sure if you would be able to see that they are from the same user and the same trip as a whole. Ya está, ¿no? Okay. So, thank you.